Okay, so if the concentration of H plus that's floating around in solution has a direct effect on ionization states of acidic groups, which means it's going to affect both structural properties of biological molecules because we're affecting ionic bonds and hydrogen bonding, and it affects chemical reactivity because it changes the protonation state of acids and bases. If that's true, then we need to know the pH of a solution. Now, the pH of a solution depends on that H plus concentration. They're directly related. But we also know that the amount of H plus that an acid releases in solution depends upon the pKa of that particular acid. So some acids release more. We also know that there are strong acids that release all of their H pluses when put into solution, and there are weak acids which only release some. Most of the molecules still hold on to their H plus. So let's look then at how we can figure out the pH of a solution of both a strong acid versus a weak acid. So let's do pH of a strong acid first. So the tried and true example of this is if you take hydrochloric acid and you dissolve it in water, you end up with H plus release to form the hydronium ion and chloride ions. So HCl is a strong acid, which means all of the H pluses on this hydrochloric acid get released to form hydronium ions. So that means if you have a 2 molar HCl solution, which has 1 H plus per every HCl molecule, so there's 1 mole of H plus for every 1 mole of HCl, then you also have a 2 molar H3O plus solution. And you can go directly from that value to pH because pH is negative log of the H3O plus concentration. So if you have a strong acid, you're talking about a hydronium ion concentration that is the same as the concentration of H plus from your acid because all of those H pluses are released. However, the case is different if your acid is weak. So let's take a case now where we have a weak acid. So we'll represent our weak acid by HA. So we're talking about dissolving now HA in water, which will release our H3O plus, or form our H3O plus, as well as our conjugate base, A minus, aqueous. Okay, so in this case, since the acid is weak, that means it has a high value for pKa or a low value for Ka. It means most of the molecules stay in this form. Most of them hang on to their H plus. So we can't go, well, if I have 2 molar HA, that does not mean you have 2 molar H3O plus anymore. You have some amount less than that because most of the molecules, again, have held on to their H plus. So we can figure out then how to calculate pH going all the way back to our original expression for the equilibrium constant. So we know that the equilibrium constant for this reaction, also called the acid dissociation constant, is the concentration of the products over the reactants, so divided by HA. And what we can do is we're looking for pH, so what we're interested in is this concentration of hydronium ion. So I'm going to rearrange this equation to solve for the hydronium ion. So if I do that, I'm going to multiply both sides by the concentration of HA and divide by the concentration of A minus. So if I do that, I get that the concentration of the hydronium ion is equal to the Ka times the concentration of the weak acid divided by the concentration of the conjugate base. So great, now I have H3O plus on its own, and that's what I'm interested in, is how much H plus is floating around. So now what I'm going to do is I'm going to take the negative log of both sides of this equation, and if I do that, I get negative log of H3O plus is equal to negative log of the Ka times the concentration of HA over the concentration of A minus. And I'm writing these values here as separate now just because it's going to make my math a little bit easier. So we know that if you have negative log of H3O plus, that is in fact pH. And then we can multiply out our negative log on the right side of this equation. So you get negative log of Ka is equal to the negative log concentration of the weak acid over the concentration of the conjugate base. And we know then that if you have negative log of Ka, that's the same thing as saying pKa. Oh, oops. Looks like I got a little carried away here. I put two negative signs, so this should just be one big negative sign. Negative log Ka minus log. Sorry, had to fix that. So if we come back, we've now converted our negative log of Ka into pKa. And now, rather than having a negative sign, I'm going to change this to a positive sign. And when I do that, that means I have to change the numerator and denominator in my log here. So that becomes log of the concentration of A minus over the concentration of AHA. So now what this allows us to do is for any weak acid, we can determine the pH of the solution of that acid given the pKa of that particular weak acid and the concentration of the weak acid and the conjugate base in solution. So that is the Henderson-Hasselbalch equation, which you saw back in general chemistry. It's horrible to spell, but it's going to be really, really important in biochemistry because we're going to be talking about a lot of weak acids. So looking at this equation, we can take it a little bit further and note that if the concentration of conjugate base, A minus, is equal to the concentration of weak acid, that means you have a 50-50 distribution, right, of conjugate base and weak acid. You have the same amount of each one. Then our Henderson-Hasselbalch equation reduces. So if we have pH is equal to pKa plus the log of the concentration of A minus over concentration of HA. So here's our Henderson-Hasselbalch. If A minus and HA are equal, these two cancel out and you get the log of 1, which means this whole term cancels out to 0. And now you get that pH is equal to pKa. So when you have equal amounts of weak acid and conjugate base, then the pH of your solution is equal to the pKa of that particular weak acid. So again, when you look at the Henderson-Hasselbalch equation here, we know that the pH of the solution is going to depend on the pKa of that solution and the relative amounts of the weak acid and the conjugate base.